We get started. So first of all, I'd like to thank everybody for coming. My name is Tim Walker. I'm the chairperson for the Sacramento chapter of SMPTE, and I wanted to just take a little minute at the beginning of this to say this is the end of our season. So this is the last meeting for SMPTE for this 2018-19 season, and as such, we've got a few changes that are happening in terms of the organization, but also wanted to reflect back on the year. We've had some great meetings. So we had Larissa from Net Insight who came and spoke about at-home productions or REMI productions, as well as IP workflows. From Sweden, yep. We had Robert Erickson from Grass Valley come and talk about case studies and IP, so actual, real-world implementations. We had a group that did a screening of technically improbable, or improbably, at the local theater. And we've had Andy Blonin from Epic Games talking about AR, and Jeff Urich from Nanosys talking about quantum dots. And we're about to close it out here with Tom from NVIDIA. So it'll be the best presentation.
We'll see.
Yeah. But as such, there's also some changes in the team as well. So the chairperson acts as his elected position, lasts for 1 year, so I'll be exiting, but will be still the past chairperson, and Dom Jackson from Xperi is going to be taking over the role. Mona Smothers will be continuing on as secretary and treasurer. She's not able to be here tonight, but good for her. Some new managers. We've got Patty Leonard, who's going to be joining as a manager. Bob Huddleston, who's always involved in some way, but he's a manager. And Sean Case. Thanks to all those new people that are coming in and renewing some of their roles. Some other managers continuing on are Scott Maddox with Telestream, Remington Maxwell from Grass Valley, and Joe Mazzi from Grass Valley. So outgoing people, Bill, yeah, you did a great job for us. Thanks for all your help in organizing these speakers. It's been a great year. Dom is going out as section manager, coming in as president. Lyle is also leaving as manager for this year, so thanks to Lyle. All right, with that, I'm going to turn over to Bob, who's going to introduce the next speaker. Thank you. Thanks,
Tim. So Tom True is a senior applied engineer for professional video and image processing in NVIDIA's professional visualization group, where he focuses on the use of GPUs in broadcast video and film applications, ranging from pre-visualization to post-production and live to air. Prior to joining NVIDIA, Tom was in application engineering at SGI. Thomas has a MS degree in computer science from the graphics lab at Brown University and a BS degree from the Rochester Institute of Technology. So with that, I'd like to introduce Tom and take it away.
Thanks, Bob, and thanks to Bill for asking me up tonight to talk about how we're taking and applying deep learning to create slow motion video. There were some jokes while we were setting up that I should rename this the deep learning for slow learners, I think it was, and then I can think of some other puns as well. This deep learning stuff can get kind of deep, so I hope I can do a good job of explaining it in that you'll be able to take something away from this talk tonight. So before I start, my colleague Andrew Page was to be here tonight, but he got called away for a work thing, so it's just me. So before I start, can I get a show of hands, like who's heard of deep learning, has a slight familiarity with what it is? Okay, a few people. Okay, good. So I'll try to explain as best as I can. So I'll start with just a quick overview of when we say deep learning, what do we really mean, and then I'll dive into the slow motion stuff, and then at the end I'll talk about how we take the slow motion algorithms that we came up with and we were applying them. So deep learning is part of artificial intelligence, and when you think of artificial intelligence, there's what we call machine learning, where computers take a bunch of data and lots of data, and they learn how to interpret that data and make decisions. And deep learning uses neural networks as a way to implement machine learning. So you think of deep learning as an implementation of machine learning based on neural networks. And these neural networks learn to spot patterns in the data and use the patterns to map from one space to another. So mapping, and so that's good for classifying images or for generating content, mapping one image to another. So in tonight's example, we're creating slow motion video. So we're taking boundary frames and generating intermediate frames. So we'll be generating new pixels using these deep learning neural networks. And while deep learning is not a new topic, it's been around for many years, dating back into as early as the 1950s, 1960s as part of artificial intelligence. The advantage of, or the evolution of GPUs, or geometric processing units, that are highly parallel floating point processing units, make it practical now to apply deep learning to everyday problems. And the problem that we'll talk about tonight is slow motion video. So this deep learning is broken into two tasks. There's a training aspect, and then there's an inference aspect. So the training aspect, you start with an untrained neural network of nodes and weighted values, and you start with a data set that represents the problem that you want to train the neural network to solve. And then you run through the training set, and you end up with a trained model that has this capability to solve the problem that you want to solve. And I'll talk about the problem sets in a minute. So the end result is this network of weights that have the highest confidence of outputting the best results for the answers that you want for the trained problem. And then this network is, like I said, it's developed with this data training set, and usually you have a data scientist, and you have your engineers like yourselves to develop this neural network. And it's iterated on to increase the performance and tuned, and you throw more data at it, you get more answers, you refine it back and forth. It's quite a big process. So that's the training part, and then there's the inferencing part. So you take the fully trained network, and then you integrate it into the application. When it's integrated into your application, then it does inferencing, and inferencing is what solves is where you apply it to new data to get the results that you want. So while the training is actually very compute intensive, and you'll see when I get into the slow motion how we spend days and days training the neural network to create slow motion video. The inferencing is very lightweight. So the inferencing you can do on a single GPU, or even there's applications that are doing inferencing on your phone, the GPU in your phone. So the inferencing is more of a lightweight application where you take the neural network, optimize, and you apply new data, and you get the answers to the problem that trained it on. So the first step when you're thinking about applying deep learning is you need to define the problem that you want to solve with deep learning. And typically what you'll quickly discover is that there's a number of techniques and multiple neural networks that you would need to apply to reach this goal, and different problems require different techniques. And like I said on the earlier slide, a good way to think about deep learning is it's mapping one problem set, or mapping a certain samples of inputs to outputs, whether it be taking images and classifying them, or taking images and creating new images. And the output of the deep learning is determined by what you want to get out of the input data. So you have the input data and you ask a question, what do I want from this data? And that pretty much defines how you will apply the deep learning. So here in what I call media and entertainment, which is kind of the space I think most of us work in, our inputs are typically images or videos or audio. And then the questions we typically ask of deep learning are, is something present in this frame, right? So that's object detection. And that's a quite common application of deep learning today that you'll see. And then if it's present, or can we actually use it for classification? What type of thing is it? It's a car. OK, well, what type of car is it? So that'd be classification or labeling. And that's quite commonly applied now in like movie studios and facilities that have large archives of data that or videos and film that they want to classify and tag so they can easily search through it, right? And then there's, to what extent is this object that we detected actually present in the scene? So that's segmentation or feature tracking. We can use it for doing prediction. And one common application of this is denoising of pixels. So we take images and we improve them by the training deep learning to actually denoise the scene and actually make the images much clearer. We can do in the world of animation, we can apply deep learning to actually create poses for characters. And then finally, can we create a new variant of images? And this is what we call object or texture creation or generation of new data. And this is what we'll talk about tonight with deep learning is some of these earlier problems like detection and classification and feature tracking. And those are, today you can buy off the software that implements a lot of these techniques. And then we're moving down the ladder into deeper and deeper problems, and we're getting into actually generating new images with deep learning now, and that's what we'll do tonight with slow motion. So to finish up, how do you determine if you're doing deep learning, if you're actually successful or not? Well, like I said, you need to first define the problem and to make sure that it's an appropriate problem to solve. Secondly, you need to train this network on data, and you need to collect the right data that's appropriate to the problem that you're going to solve. Because what you'll find out is you're training this neural network to do something, but if you train it on the wrong data, you're going to get the wrong answer. And then you need to ensure that the ROI is there, because it takes a lot of data and a lot of training and a lot of refinement of the network to actually get something that's actually usable and solves the problem and can be trusted to solve the problem at a high percentage of the time. So there's always the ROI to think about. So this has just been like a brief overview of deep learning, and now I'll go forward with how we've taken this deep learning approach and we apply it to slow motion. So why doesn't the video play now?
It's very slow.
So I should have tested this. So anyway, if I could play the video here would show that we're generating slow motion is doing temporal interpolation between frames of video. So here in this video, with the goal of it is to show the temporal detail, right, between the frames. So here we can apply our approach to go from 1x to any number of frames in between. So that's kind of the goal of what we're going to try to solve tonight. So let's define the problem that we want to solve, because like I said in my introduction, the first step of applying deep learning is to actually define the problem. So the problem in our case is multiple frame variable length interpolation. So between any two input frames here, T0 and T1, we want to generate n interpolated frames. And these could be any arbitrary number. So that's our goal here. And how is this different from traditional single frame interpolation? Well, single frame interpolation, you're taking the two input frames and simply generating the intermediate frame, a single intermediate frame. And there are actually quite a few deep learning approaches that can do this. It's simple single frame interpolation. And if you want to generate multiple frames, like our problem, the problem that we're trying to solve, you can just recursively apply this technique. But there's issues with that. And it poses a problem for a real-time application, because in real-time application, you have to generate this frame, and then you have to generate these two frames. Well, the problem is that this is generating the frames out of order, and this doesn't work if you're trying to do this in real time. Also, let's say the network is trained to generate the frame that's in the middle. Well, now you want to generate two frames. And for that, you'll need to totally retrain the network. So that's the other part of the problem that we want to solve here, is that we want to be able to generate an arbitrary number of frames. And we can do it in the correct order. We can do it in the reverse order. Or we can actually, the algorithm will do them all at one time. And we can also, if there is the case we only want to generate a selected number of frames, it's very flexible. So our implementation is called what we call super slow-mo. So this technique is based on a paper that was published by NVIDIA Research and presented at the CVPR Computer Vision conference last June. So that's where the basis of this presentation. And we've taken this, and the next few slides I'll go through the implementation, or how we do it, and then at the end I'll talk about how we've taken it and we've put it into an SDK that you could actually download today and apply videos and do your own slow motion. So the basic idea is to use optical flow to synthesize frames. So given two input frames, we want to interpolate the accurate, if t is anywhere between 0 and 1, we want to be able to accurately interpret the frame at that location t. So for each target pixel, we want to know its corresponding pixels in the second frame and the first frame. So if we know the correspondence, we can then infer the appearance of the pixel here. So take what we know about the pixel here, what we know about the pixel here, and infer what the pixel value is here. But just knowing this correspondence isn't enough. We also need some other information. We also need to know if the pixel is visible or occluded, of course, because like say for this particular pixel here, we can see that here it's visible in the initial frame, but in the second frame it's occluded by the car. So there's two problems that we need to solve here. We need to first solve the correspondence problem, or the motion of the pixel from between the two frames, and interpolate that. And then we need to solve for the visibility in the cases that a pixel is either not visible here and then visible here, or vice versa. So if we look at the first problem, it's what we call optical flow, or the correspondence problem. For those unfamiliar with optical flow is the 2D motion from the first image to the second image. And it's kind of showed by the color key here. So if the motion is to the left and down, then it's this green color. Up and to the left, it's blue. Up and to the right, purple. down and to the right orange. And then the intensity is how strong the motion is. So this is optical flow is a classic computer vision problem. So given the two input frames that we have, we want to estimate the motion of every pixel from one frame to the next. So looking at the video input here, we can see from the optical flow that the car is moving, because it's green, it's moving down and to the left. And with the saturation indicating that the significant motion is the car itself and not anything of the surroundings. So there exists already a lot of good deep learning solutions that'll determine the bidirectional optical flow between two images. So this isn't new work here. We can use FlowNet or FlowNet2, SpyNet or PwC or a bunch of other already produced convolutional neural networks that'll, given two input frames, will give us the bidirectional flow. So we'll just take one of these off the shelf and we'll use that. But our use case here in super slow-mo is slightly different in that we want to know the motion from an unknown frame back to the first frame and forward to the second frame. So how do we figure out the motion here, or determine the motion when one of the frames is actually missing? So if we look at the problem in one dimension, so each column here represents an image. So here's the image at time 0, and here's the image at time 1. And each of these dots represents a pixel in each of the images. So we can use the neural network to learn the forward motion from F0 to F1. So the forward motion of this pixel between this image and this image we'll call F0 to 1, and the backward motion of F1 to 0. This is a no-brainer here. This is just applying an off-the-shelf convolutional neural network to give us this optical flow. But what we're really interested here is the motion from this pixel here in the target frame, t at time t, to the corresponding pixels here, ft0 and ft1. So we want to know the forward motion from here and the backward motion from here. And we can make the assumption that this motion between these two frames is what I'll say kind of symmetric. It's opposite in size, but it's equal. We'll say that it's equal in magnitude between the two images, but one is motion backwards and one is motion forwards. But we still need to generate one motion vector to describe this pixel. So the solution is to actually borrow from the bidirectional optical flow. So if we see that this pixel is kind of at the same spatial location as these pixels, we can approximate the optical flow backwards by taking this time t and multiplying it by this motion vector here. This gives us a reasonable approximation of the backward motion from this unknown pixel location back to the first image. And then we can do something similar for the forward motion. This time we'll apply 1 minus t, which is, so if this is t, then this is 1 minus t, to this vector, the forward motion vector. And then if we switch the sign around, we can get the reverse motion vector that we need. And then if we can linearly combine these to give us the final motion vector. And if t is small, we get this bilinear combination here. And if t is small, then we know where this, if t is small, then the forward motion plays more of a bigger role in the determination of this pixel because it's closer to the first image. And if t is large, like we're way over here, then the the reverse motion has a bigger play in the calculation of this pixel. So we make this bilinear combination of these two approximations. So now our network looks like this, where we take the input images and we get we have our bidirectional flow. Then we take and we add this flow approximation onto the end of it. And this is what we call deterministic and parameter free. So we can take the output of a convolutional neural network and add this flow approximation, and it doesn't add any more variables to our algorithms here. We have t, and we have the motion vectors. There's no additional parameters. And this is classic deep learning. We took the output of a convolutional neural network and we added another layer to do some other calculations and modify the data that this convolutional network spit out. So we made this assumption that the motion field is smooth. So the motion was fairly constant between the pixels in the first image and the second image. But how good is this approximation? And what we find is that it works well if this motion field is smooth, both the forward and backward motion. But if the motion field isn't smooth, then we have a problem. So if we look at some realistic motion fields here, so we have different things going on here. We can see that motion is smooth across like surfaces, but where there are two surfaces, one moving and one not moving, there's a motion discontinuity. And this motion discontinuity breaks down our assumption that the motion is smooth, and it breaks down our calculation of these motion vectors of the optical flow. So here's kind of the problem back in our 1D solution. So we have a motion boundary here, so a boundary between an object that's moving and an object that's not moving. So we have a pixel moving downward and a pixel moving upward, and we want to calculate the motion we want to calculate this target pixel here. So if we look at the forward and backward motion at this spatial location here, we end up with these two vectors that are going in opposite directions, and this introduces a lot of error in our approximation. So we're going to add up with a real bad approximation at this pixel, and it's going to, at the end result, we end up with aliasing and a lot of noise in the scene where you have an object that's moving next to an object that's stationary. So how do we deal with these errors in our approximation? So the solution is to refine the flow. So again, classic deep learning, we're taking and adding another layer into our network or into our algorithm to take results and refine them. So we take the flow approximation that we generated with the input images, the flow approximation, and we put the input images through the flow approximation to produce these warped images. Then we apply another neural network that gives us a refined optical flow, which it refines the flow so that we don't have these. There's not so much blurriness between objects that are moving and stationary. So let's see an example of how this works. So here we have the input, and the original optical flow shows that we have a lot of this is good in most cases, but it breaks down when there's errors across motion boundaries. So then we refine it, and if we look at the difference, we can see that if we subtract one from the other, that the intermediate refined flow is much sharper edges, and it will give us much higher quality results in our slow motion images that we're going to generate. So we have much sharper motion boundaries. That's kind of the goal here. So if we go back to what our network looks like, we have this refined optical flow, and we also use this network to give us visibility maps so that we can tell, to solve the visibility problem that I talked about in the beginning, where we have a pixel that might be visible in one of the input images but not the other. So now that we have this refined flow and the visibility maps, we can go ahead and predict our frames. So here's an illustration of how our algorithm works now. So if we given the input frames here, this is the t equals 0, t equals 1. We get our intermediate optical flow, and then we warp the images through to get the refined flow and generate the visibility maps. And then if we apply the visibility maps here, we can through our warping function, we can warp the refined flow and take the warped images and use the invisibility maps to refine the resulting images. And you can see here that when we have, it's hard on this projector, but with the visibility maps, the edges are much cleaner than when we don't use them. And I have some examples later where you can see where the algorithm breaks down when there's periods of high motion. So, but here the football player's, or the player's arm is moving down, and what's black here is missing in this frame and present in this frame. So you can see without the visibility maps that it's very blurry here. So our overall architecture at the end of the day looks like this. Given the input images, we use a convolutional neural network to compute the bidirectional optical flow. We take the input images, we put them through this flow approximation to create the warped images, which then generates a refined optical flow, which we then process with the visibility maps to give us the frame prediction. And so that's kind of the overall architecture. So when you're thinking about deep learning, that's like step number one. We've gotten from our input to our output. Now we have our convolutional neural network, or in this case, it's a combination of two convolutional neural networks. Now we need to take our training data set and apply it to train the network so that we can actually use it to generate slow motion video. So how did we train this network? So we used a collection of high frame rate video at 24 frames per second. And essentially, a lot of you guys work in video. There's not a lot of high frame rate public domain video out there. We're a GPU company. We make GPUs that people play games on. We don't have an archive of high frame rate video that we can train on. So we went out on YouTube and we collected pretty much every piece of 24 FPS video content that we could have. And it's like, I have the data on the next slide, but it's a small number. And we downsampled this, so we divided by 4 to get 60 frames per second video. And we applied our architecture, our convolutional neural networks, to the subsampled, temporally subsampled video to generate the missing frames that we took out, right? And then we compare the frames that we generated with the frames that we took out, and then we refined the network weights to improve the results. And this technique is called what we call a GAN, or a generative adversarial network. So it's actually a combination of two networks. So this would be our network over here. It's called a generative adversarial network because you have a network that's generating the results. In this case, this is our dual convolutional neural network that I just talked about. And then there's another neural network that's the discriminator. It's looking at the results and comparing them to the ground truth, which in our case is the images that we removed from the original 240 frame per second video. And then it feeds back into the original network, tuning the weights of the convolutions of the nodes in the convolutions to improve the results. So we call this a generative adversarial network. So there's a forger and a critic, and this is generating images, this is looking at them and judging them and then feeding back. And then this is still the network that you deploy. This is just a network that's used for the training. Yeah. So here's kind of the performance. So we had 300,000 frames of video. So it's not a large number. It might look like a large number up here, but when you get into deep learning and start training networks to do things, you want to throw as much data as you want at it. And this is a small number compared to, like, we go and we talk to a television network about applying deep learning to video, or one of the movie studios. They have like tons of content where we just used content that we took basically from YouTube. So on 6 GPUs, it took 6 of our high-end Volta class GPUs, which is pretty much state of the art. It took 10 days to train the network. So like I said earlier, the training is quite computationally intensive, and it take quite a while. But then the inference is fairly fast. So to generate 7 slow motion frames between 2 frames, we can do that in 360 milliseconds, which is 5 or 6 milliseconds per frame. So the actual inference is fast after all the training is done. So this isn't too bad. But it's still not real time, right? I mean, not when a single frame of video is 16 milliseconds. So there's work to be done, but this is kind of the ballpark that we're in right now. So that's kind of an overview of the algorithm. That, like I said, it was originally developed by NVIDIA Research and presented at CVPR, and then we've taken that and we've integrated it into an SDK. But before I get into that, I want to just talk to you about the fact that at NVIDIA, we're not the only ones that are looking at slow motion video. And actually, at NVIDIA, we actually were looking at it first in the game space, in that for esports and for other gaming events, people want to slow down they shoot all this high frame rate video, and then they want to slow it down so they can see more detail, right? So it was originally done more in the game space. But then we thought, oh, this would be a cool application in the professional video space, so that then we started looking at it as well. But also, we've been working with EBS, and EBS has been researching applying deep learning for slow motion video as well. So I wanted to just bring this to your attention that other people are looking at it. So EBS has what they call an AI engine that uses a neural network to generate the multiple intermediate frames, as I described in the problem statement. And EBS presented some of their initial results at NAB in April this year. They had a tech talk during the broadcast conference. And we've been working alongside with them. Their AI engine here implements their own neural network from their own research, but they also have taken our SDK that I'll talk about in a minute, and they've been comparing the results, and we have a con call every week with them, and we talk about techniques and how to make it better. And it's kind of interesting talking to them because they're approaching it from a broadcast production point of view, mainly for sports, and which is more of a real-time application of it, where we've been looking at it more as an offline activity, where, okay, you're going to take this slow motion engine and plug it in, create a plugin for After Effects, or I mean for Premiere or some other video editor application, and do it offline versus online. So it's been quite interesting. So in a production environment, EBS sees like 2 places where it works, right? So in the first application of it, they take their AI engine and they put it in the pipeline after the replay server. So and in this case, you're generating basically the replay, the slow motion in real time, taking video off of the replay server, generating the frames real time, adding all the other time codes and other stuff that you need to send it to the live to air or whatever. And so this is one application of it, and this is like a goal, because from a performance point of view, we're not at a point at NVIDIA. We're not at a point. EBS isn't a point where we can do this in real time. But it's interesting that they're thinking about it in this way, because it's a way that you can create slow motion and not have a special slow motion camera, or it might be at a remote location where you don't have the slow motion equipment or whatever that you would need to generate the video. And then they also, the second application of it is to attach it to regular video, right? And then this is more of an offline application. You create the slow motion video and you put on a replay server to play out at some later time, right? So this mimics the behavior of having a slow motion camera, but with a regular camera. So it's a way to save cost, or perhaps you don't have the slow motion camera at this location, or perhaps you're trying to generate slow motion video from archival footage or something like that. So NVIDIA NGX, we took the original research that NVIDIA Research did, which was done in PyTorch, which is a Python. If you're familiar with Python, it's a programming language, and PyTorch is a deep learning framework that's written in Python. So it's fairly easy to use if you're familiar with Python, and it's a common starting point for people that are getting into deep learning. So we took this originally written in Python and we ported over to cuDNN, which is a deep learning framework that's built around CUDA, which is NVIDIA's computational programming environment for the GPU. And then we integrated into this SDK that we call NGX, which is basically an SDK to integrate deep learning into creative applications like Adobe Premiere or Photoshop or After Effects or other applications. So because we wanted to make it easy for applications to integrate some of these deep learning techniques. So deep learning is just one of the techniques, slow motion is just one of the features. It also includes up-resing, so you can feed it low-resolution video. You get up-resolution video, again, using a different convolutional neural network. Infilling, or wire removal, removing mic booms and other things from scenes automatically, and also high-quality anti-aliasing. So the way the SDK works is we do the training. So you download the SDK, you integrate it into your application. We've done all the training. So what you're downloading is the fully trained network ready for inferencing. So we've done all the heavy lifting, and now you have this fully trained network that you just integrate into your application, and then you can apply it to the images or the videos in your application. And then the next time you use the SDK or use that feature, like you want to do slow motion, it goes out on the internet and it finds to see if if there's a newer trained model network to download, because we're constantly training the networks and we're posting newer trained networks. Just like when a software application, you start it up and it notices there's a new driver on the internet and it asks you if you want to download a new version of this driver, or you want to use Skype, and there's a new version of Skype available, or whatever. It kind of works the same way, which isn't always a good thing. We know that, but anyway, it's to make it easier to integrate deep learning into your application. And we have a versioning system, so you can actually, let's say you're working on a feature film and you're using this trained network, this version of the trained network for slow motion, and you want to be consistent through your whole film production, then you lock your application to using this version, so it won't go out on the network and look for the new version. But anyway, this is what this SDK does, and it's basically, like I said, being able to take a feature like slow motion or up-resing video and integrate it into your application using deep learning, and not have to do all the training of the network and all that stuff on your own. So let's look at some of the results. This is going to be interesting because the videos don't play, at least on my computer. Anyway, so we get fairly decent results, and I'll get into the quality in a minute. It's not real time. It's roughly 5 or 6 milliseconds per frame for, this is 720p video material. Currently, some of the current bottlenecks is it takes a large amount of GPU memory. So we're actually taking the cuDNN implementation and we're converting it to use TensorFlow, and it should be much more efficient. So we should be able to generate, we should be able to apply it to 4K video coming up soon. Currently we're doing 720p and 1080p type video. I can show these videos afterwards, I believe. I'm not sure why they don't play right now. But and another cool application of slow motion, of this synthetic slow motion, is if you take existing slow motion video and you slow it down even more, you can get even more detail. So actually, that's one of the results that we found, is that if you take an application like Adobe Premiere or some other applications that have optical flow slow motion built into them already, and our deep learning approach isn't that much better than what's already out there, but if you slow it down even more by applying it to slow motion, then it's actually, you can see a lot of super interesting stuff. So we've had, if we think about the quality, there's a couple of quality issues. Again, these are results. These slides are from EVS presentation, but we see the same behavior in our implementation versus their implementation. When objects move too fast in the scene, or the camera pans too fast, there's excessive motion blur in the objects, and this is kind of a big problem. And if you think back to the algorithm, again, it's areas of high motion against an area of no motion or little motion, and the time steps are too fast, and the optical flow isn't refined enough. So yeah, you end up with this high motion blur, and the solution that EVS uses is they apply some post-processing to do sharpening based on the exposure time that they're slowing down the motion down to. We think we should be able to solve this with better training, or more training using training data that's more applicable to the data that we're actually trying to slow motion. So if you train the network on, if you're going to do slow motion for sports video, you want to train the network on sports videos. And then the other issue is quality. So here in this football scene, you end up with missing information because this is one of your frames, and this is the other frame, and so this is the frame here, and the network wasn't trained on American football, so it doesn't know what to do when it generates the frame here with the football. Does it go under the line or over the line? So there's a lot of issues like this, which again typically results from objects moving too fast, and we're actually missing information. But these could be resolved if we did more training with more appropriate content. So here's an example. Again, it's hard to see here, but this guy's arm is like missing. And that's because we trained on 300,000 YouTube videos, but none of them were a guy doing jumping jacks. If the guy was doing jumping jacks, this probably wouldn't be a problem because the network would know how to deal with this. So how are we looking to improve the quality? So basically, more training data at a variety of frame rates. But like I said, the way we train is we we take the original frame rate, we remove frames, so we temporarily subsample it, then we generate the frames, then we compare the generated frames to the frames we removed, and then we train the network that way. And then more application-specific training. So if you're going to do sports, you want to train to sports videos. And more than that, if you're doing American football, you want to train the network on American football footage. If you're training for soccer, you want to train on soccer footage. These are some of the things that we're finding out as we go along. And then there's typically some post-processing filtering that needs to be applied when you're generating slow motion video to deal with the temporal, that has some relationship to like the final frame rate. So that's pretty much an overview of where we're at with slow motion, how we've taken slow motion and applied deep learning to generate, how we've taken original video, used slow motion to generate, used deep learning to generate the intermediate frames for slow motion, and it's multiple, any number of frames between two input frames, and it's fairly flexible. What we're working on now is performance, because we want to really do it in real time or close to real time, and we want to be able to do it on 4K footage and probably soon 8K footage, and it's very memory. It's very high memory intensive, so we need to refine the networks further, and that's a big part of deep learning. Sure.
So how long is the typical retraining sequence? So for example, as you mentioned, a video that guy with jumping jacks would be much better if something provided you with a video of somebody doing jumping jacks. So if I'm a guy who owns a company that's got video of guys doing jumping jacks, and I don't like your results, and I give you 240 frames per second video of what it should look like, and you go back and retrain your neural network to produce better results for me. How long is that cycle from me giving you a sample of what it should look like to you giving me back a better trained neural network, generally speaking?
That's a good question. It's not really defined at this point because we're kind of in the experimental stage, but it could be like, so we add your videos to our server or our disk farm that has all the videos, and it just gets added to the training, and we keep retraining it. And then I'm not sure how, logistically, how often we push out a new network. But if yeah, it's like days. Because like I said, it took 10 days to train the original network. And you're not really starting at ground zero anymore. You're starting with what you have today and then just doing additional training. So you have 10 days in always already.
So you're building on the same neural network always?
Yeah.
And just adding more stuff?
Yeah, just adding more training data. Unless you get to a point where you trained it on some bad, like, if you trained it on some bad data, then you're going to, like, you get garbage in, you get garbage out, right? So you probably want to have a network that's trained just for sports and a network that's trained just for drama or animation or whatever. So, but we're not quite at that point yet. And ideally, where we want to get to is we want to give you a network that you can train on your own data. So if you're a TV network or a movie studio, you don't want to give us your data because it's your intellectual property. You want to train on, you want to be able to train our network on your data and give our network back to us, or keep our network, your version of our network. And that's kind of what I'm going to get into here under the context of how do you get started. But the question that, the first question we always get is, okay, I have all my data and I want to use your SDK, but on my data. And the answers to that are kind of in the next couple slides here. So how do you get started? So say you have a problem that you want to solve. Like, deep learning is interesting in that it's a technique that's looking for problems, and then the people that have the problems are the people like you in the room that have the problems, but you're not an expert in deep learning, and unless you're a data scientist, you probably will never be an expert in deep learning. So that's kind of where we are right now, and that's kind of the biggest problem to solve. So if you look at deep learning, it's complex to build the network, then train it, and then test and maintain it. And so we've been trying to look at ways to remedy this learning curve and accelerate the deployments. And so we've come up with these things called what we call deep learning containers. So in these containers, you download a complete environment where you can take a network and train it on your data to solve your problem, and you don't need to think about all the other pieces that you need, the network, the compiler, the this and that, to do your deep learning research. So all the top deep learning softwares such as TensorFlow and PyTorch I talked about, and TensorRT, we have these tested and tuned and certified for high performance in these containers that run in the cloud, or they can run on a GPU in the workstation next to your desk, or on a collection on a cluster. We have these all set up. We call these, like I said, deep learning containers. And these are different from, if you're familiar with virtual machines, where you log in and you go off on some server somewhere and you create a little virtual machine, which is your kind of workspace. These are much different than that, in that you're working on your system here, or you're working in the cloud, but you're basically grabbing a fully functional working workspace that has all the parts already there. You're just going to use it, and it's yours. And the way you do this, some of you may be familiar with what we call Docker, which is a GitHub repository project. And you install Docker on your system, and then you download these containers within Docker, and then they're there for you to use. And these containers are all hosted in what we call the NVIDIA GPU cloud. So you would, like I said, you would download these containers. They're self-contained and they're portable, and they can pretty much run anywhere. So you can build, train, and deploy a deep learning network on your desktop, or in a data center, or in the cloud. And let's say you had an idea for a deep learning project, you could run it on your GPU at home on the weekend, but then when you want to run it at speed, you can just bring it into the office and run it in the data center, or in the cloud, or somewhere like that. So it's a way to get started without having to do quite all the heavy lifting. So to answer to get back to the training part, the NVIDIA GPU cloud kind of interface kind of looks like this. And I don't want to do a big marketing pitch. That wasn't my goal here. It was more about the training. But it's free to use. You just create a login, and you can go in there and you can download all the networks already built into Docker, and then you can do anything that you want with them. But to get back to where I was going with the training, the idea here is that you'll be able to download the slow-mo network, for example, in a Docker in your premises, and then train it with your data, and then you can either give it back to us or you can keep it. So I guess what I'm trying to say is we're building this infrastructure out now so that you can do that, because at least in the example for slow motion video, when I go to talk to people about slow motion video, like I said, the first question is always, how do I train this on my data? I don't care about your data. So this is how we're getting there. It's just not there yet. The screenshot here is how we're training. We have some deep learning applications in the medical space, and this is how this is how the medical stuff happens. But eventually you'll be able to see the slow motion here, train network, and you can just grab it from there. So that was kind of my pitch on slow motion. I apologize that the videos didn't work, but that's kind of where we're at with applying deep learning for slow motion. So if there's other questions, I'd be happy to answer them.
You know, basic newbie question.
Uh-oh.
You talk about making a network that you can then plug into the inference process.
Yep.
I'm envisioning this network that you're downloading or making or whatever is a pile of binary data that's going to the inference engine.
Yep.
As you apply more training and it gets smarter, does this pile of binary data grow? Does it just keep getting bigger as it gets more and more training? And
No, when you're training, you're just refining the weights. And the weights are like a three-dimensional matrix. So there's a weights file, and the weights file is it's just a binary file of three-dimensional values that get loaded into the nodes of the neural network. So the weights just get refined. The weight database doesn't get bigger unless you add additional layers to your network. So I didn't go into too many of the details of a convolutional neural network, but it's based on convolutions, right? So you apply convolutions which downsize things, and then you upsize. It's applying and reapplying convolutions, right? So you have weights for all the values, right? Like applying a filter to an image. So if you add additional layers of convolutions, then you add additional weights to this file, but otherwise it's the same size. But they are quite large, yeah.
As one applies new training stuff, you mentioned the ball or the guy who was juggling fire, does that basically displace some training that it's already had, or?
Yeah, it modifies the values.
Water it down?
Well, it depends. Again, if you had a nicely trained network for juggling, and then you applied a whole bunch of videos on car racing, you're probably going to deteriorate the results of your juggling network.
So doesn't that mean that likely you're going to have, almost the same thing, you're going to have silos of types of material?
Yeah.
If you talk about weights in hidden layers between receptors here, they are single value weights. And so if I give you the fire jumping jack dude,
Yeah.
and material, and I say, this is the perfect solution, you give me a trained neural network. There's only so many weights because there's only so many receptors and there's only so many layers.
Right.
So they've got to be replacing what was there. So surely that means you have to have genres of material that people have to be smart about in saying, I'm going to use the model that does jumping jack fire eaters, but not football.
Exactly.
And just choose between them. As we move forward, I'm sure that's where you're going to end up. You're going to have these individual silos, surely, of types of material that you do a good job with.
Well, and if you talk to deep learning people, they'll say no, that one network should do it all. But what we're finding in our industry here is that, yeah, the network needs to be trained on the specific data that you're applying it to. Yes.
But couldn't you use classification ahead of it to pick the right
Well, that's exactly what I'm saying. You'll have to be silos of
you could use deep learning to
I'm
get to the
doing
right
fast
side.
motion football. American football. I'm doing car racing, like Formula 1 car racing, and presumably choose the right initial model to start the workflow. Because I can't see that the weights for fast-moving Formula 1 cars will not all match somebody playing badminton in Pakistan.
That's probably
Not that you need to slow down badminton, just so you know. Well, cricket, 5-day game. Well, nobody knows.
Yeah, let's make it slower.
Yeah, can you speed up the baseball game?
No, I was actually going to ask a related question. Why is this called a slow-mo technique? Because it seems like you could use the exact same thing to generate, video frames that play back at 2/7 of the original time.
Yeah.
Is there any problem?
No, it generates arbitrary frames given two inputs. So, yeah. So we're using it here for slow motion, but it could be used for other purposes.
So I'm assuming the temporal between these two frames is so small that the variable speed between frames is okay to ignore, because it could be moving fast in the previous frame and slower in the second frame, and the rate of its change could be different depending on where that intermediate frame is.
Yeah.
So is there a plan to have it extend further than between two frames? To find the trajectory into this frame and out of that frame to find a more precise intermediate frame?
That I don't, yeah. In the deployment that we're working on now, The answer, the answer is no, but what NVIDIA research is doing, I'm not sure.
It looks like this is piecewise.
So
Yeah, this
it's
is-
between two frames.
Yeah,
It's
yeah,
technically one.
yeah.
But those two frames don't have to be separated by one predictable frame.
No, they could be, it's any two frames, so, I mean, you could, yeah.
There could be acceleration between these two frames that's not present in the next two frames.
Yeah.
And so there would be a discontinuity between that frame between the two frames.
Yeah. Yeah, I mean, yeah, our goal wasn't to put the slow-mo camera people out of business. It was a unique approach to creating slow motion. It doesn't always work in all cases.
I'm sure within the time frame of frames we have available, it would be perfectly fine to ignore
Yeah.
that trajectory type of thing.
Well, not just dealing with motion, but also dealing with stationary but changing levels of intensity of light. How about an accelerating cop car with a flashing light? How would you deal with that?
That's a good question. I haven't,
Now you can see it bead.
we haven't tried it on that. I'll be honest with you, a lot of the footage that we've been using is stationary camera, and then, yeah, the environment. You saw the fire juggler is kind of like the most aggressive stuff that we've been using. We haven't done a lot with like fireworks and flashing lights and things like that.
Can the same trained network work on different frame sizes, frame geometries, and can then also handle progressive versus interlaced video? Or does interlace just kind of throw a monkey wrench into the whole thing?
Yeah, it's funny. When I started working on taking the NVIDIA research stuff and putting it into the SDK for production, I asked all these same questions because all these research guys, they don't even know what interlaced video is. So, and then they do everything in 8-bit, and we have 10-bit and 12-bit, and we normalize, and they don't. Anyway, the short answer is it's trained on progressive, and it works best on progressive. Yeah, interlace kind of throws it off, especially, well, more like in sports, in things where there's high motion, for the same reason why we like have progressive scan TVs for sports now instead of interlace. So it gets thrown off with interlaced video.
Is there any weighting in the inference engine, or is that a pretty static algorithm that just interprets the trading?
Yeah, it just takes the weights from.
It's really just a single sort of entity.
Yeah, it's a single entity, and we've cut out we've tuned it and cut out layers that aren't used for performance to make it high performance. And that's actually where a lot of because ultimately we want to do this in real time, not just this problem, but any problem that you apply some kind of automatic algorithm to. Typically, it's a real-time process or greater than real-time if you're doing compression or something, right? So, yeah, so it's always removing layers to get rid of redundant results or things like that. But yeah, it's just weights, and these are just loaded into the network.
Is there a reason that everything you downloaded off of YouTube was in 24 frames?
Well, I didn't do that part of it, but that's probably the highest frame rate stuff that we could find. It was more, again, the NVIDIA research stuff. And then, I've been working through SMPTE, I was working with Jim DeFilippis, and he was working with one of the universities in Texas, and they were doing all this high frame rate research, and all their stuff was 240 frames. So I assumed that was kind of like the highest, except for like extremely special cameras. I'm not a camera guy. I assume that was like a standard high frame rate standard, and it's easily divisible by 4 to get to 60 FPS, and then it's kind of easy to work with. those are just conclusions that I came up with. I don't know how much true that is.
Are there any techniques in the works that'll work from 2 previous frames to generate the next possible frame? In other words, not between 2, not interpolating, but predicting frames.
Yeah, when I went through I haven't seen it applied to video, but when I went through the beginning, the little table that showed different applications of deep learning, there's this pose estimation. So in the animation space, there's people that are taking deep learning to estimate the poses of characters, and I assume that could be extended to do video as well. I mean, it's just training and.
Yeah, I was thinking of like in VR, you have asynchronous time warp, which tries if your frame rate can't generate a frame, it guesses one. And I don't know what techniques.
Oh yeah, well in the gaming space we've played a lot around with that, and more on the gaming side of NVIDIA to try to estimate frames yeah, the results are mixed at this point on stuff like that. And then we've done for ray tracing or high quality rendering, we've done the noise reduction where you render so far and then you let deep learning just finish it because it's actually faster than ray tracing or final frame rendering the whole frame. So that's kind of a prediction model as well.
I wonder if is there any sort of diminishing returns? You know, you can sort of test with maybe a super high frame rate camera and sort of test to see, okay, at what point are you just churning data and not getting an increase of an improvement in results? Is there sort of a sweet spot at which you can say, right, we've done enough, this is good enough, or we keep going for another 10 days, but we don't really get that much accurate?
Yeah, I don't know the answer to that. I know that we have these results today and we're not super happy with them. I mean, there's the quality issues that we talked about, and we want to make the results better and also be real time. So we're kind of working toward that goal. And to us, it's just more and more training, and the training data is really hard to get when you don't have like I said, when you don't have an archive of data. So yeah, we haven't gotten to a point of no return yet, I guess is what I'm trying to say.
Back to the training phase, Paul's original question is every single clip of the 300,000, is this going into one round of analysis, interpolation, comparison, or dozens, 100,000 times?
Thousands of times, because you train it and then it's a constant refinement, right? So.
And do you have an idea of the data, how much data it was, the 300,000?
Well, for the original research, it was the 300,000. That was 300,000 frames of video. I think we've gone past that now for those statistics were for the original research. We're in this production of this SDK now, and we've added some additional data, but we're still high frame rate data is very difficult to acquire if you don't have an archive or a camera or things like that. So.
When you do new training, you don't do one task. You don't give it a clip and try once, say, okay, now let's fix that. I believe this is correct, so correct me if I'm wrong. You try it, you make an adjustment, you try it again.
Yeah.
Much better with that. You try it again.
Yeah, it's
so you iterate and iterate and iterate.
Yeah, it's that it's the adversarial network, right? So you put the training data through it, you compare the results to the ground truth, which is the original frames, and then you tweak the results, and you do it again, and you tweak it, tweak.
Grossly on the entire picture, the entire picture gets slightly worse, and this one part of it gets better.
Yeah. Yeah. So that's how the training works.
Tom, are you able to run your videos on your
No.
slides? Then I saw a little play button in the bottom of the mouse.
No, it's interesting because Yeah, I couldn't run them the other day, but I plug it into my HDR monitor on my desk and then I can run them. So it's kind of weird. Let me just disconnect the... Yeah, so it's the projector. Yeah, if I unplug the projector, then they work, so... Yeah, so let me show you some of the results, then I can just put my computer, turn it around. Or maybe everyone can come up and look at it. So.
So I'm sorry to ask maybe two simple questions. Once you have this training done,
Yeah.
and you have something that's trained, and I have video footage, I want to apply that slow motion technique to it. Do I need to replicate this network and run it? Or is there just some delivery of algorithms that you get that you just run on the computer and on the conventional computer?
Yeah, so that's the SDK that I talked about. So we call that EdgeX. You would download it. It comes with a sample application that I wrote that you can just feed it an MP4 file and say, I want n number of frames between every frame, and it goes off and spits out those frames and generates a new MP4 file.
But does that generation of frames just work on your local computer with conventional?
Yeah, it requires...
Do you need to model this network to make it work?
No, it works on a GPU, one of our last 2 generation GPUs. I could actually run it on the laptop here. But yeah, it doesn't do it in real time. It's like 5 or 6 milliseconds per frame. And if it's a big, faster GPU, it'll be slightly faster, but not real time. And it would be slower on a slower GPU. But yeah, you can, I mean, that's our goal, is that the training is done in the data center or on a cluster of GPUs, but the inferencing should be able to be done on an edge, what we call an edge device. So a laptop, a phone, like we have all these edge devices between 2110 and other things now, you know, video things. Someday we see being deep learning algorithms in those kind of edge devices, right? They're embedded GPUs or whatever, so.
How specific is the training? For example, you had this guy with the jump, and you said if you had somebody doing jumping jacks, it would have been better.
Yeah, because he's waving his arms. So the network would learn, the training would keep training on these moving the arms and comparing the missing frames with the frames it generated with the original missed frames that were taken out, the original frames, and it would learn that there's this up-down motion that it needs to account for.
So if I had a guy doing semaphore,
Yep.
I could use that video also.
Yeah. It wouldn't have to be jumping jacks. That was just an example.
You had to be with this.
Well, the guys at EBS will tell me that, like I said, for American football, it needs to be trained on American football, and for soccer, it needs to be trained on soccer. Don't try to mix them, because the results, you get results, but they're not as good. So.
Any different in compressed video versus uncompressed video? Is it pretty much the same?
Yeah, the whole algorithm works on images, so it all depends on the quality of the original image. So we're doing H.264 MP4s. This takes, it's kind of weird, because NV research guys, you know, we work in normalized 0 to 1 floating point FP16 or FP32 numbers. They like to work in floating point. Maybe this is TMI, but floating point numbers from 0 to 255 and some other weirdo things. So we have to do this conversion from this data format into that. But at the end of the day, it's RGBA data, and you get RGBA frame out. So whether it's compressed image or SDI uncompressed video, it doesn't matter. It all depends on the quality of the input that you were trained on, and then the inferencing data as well. But it's just for ease of distribution of the SDK and to provide simple samples, we use the codec that's in the NVIDIA GPU in our sample program to decompress the H.264, feed it to the network to generate the new frames, and then we can re-encode and create an H.264 on the output. But at the end of the day, it's working on uncompressed frames. So it wouldn't even need to be video. It could be any 2 frames. I mean, another application of this is animation, right? And you can take 2 keyframes and have this network generate all the intermediate frames instead of having an artist draw them, right? So, or use some other software.
But the intermediate frames of your algorithm would be equidistant between those 2 frames. And if there's activity that has an acceleration at the start of the frame, at the end, it would lose that.
Yes.
Are there any working examples of this that are published now that we can check out and see?
Yeah, so the SDK I talked about has a sample application that you can use with MP4s. The EVS stuff is kind of researchy still. Who else is using it? Yeah, I can't talk about anyone else that's using it. Most people, I'll be honest with you, in relation to the slow, I'm talking about the slow-mo stuff. Our SDK also includes the upresing and the wire removal and other things. We have, I'm just talking about the slow-mo. We have people looking at it, but again, they want to train with their own data, and we don't have the infrastructure in place to do that yet. So yeah, other than the sample application, not anything that I can share with you.
I think what I'll do is save questions. We'll finish up the meeting, and then you guys can come up and ask.
Oh, you guys have to have a meeting.
Yeah. But so I'd like to thank Tom for the presentation. Very interesting subject, and we have a plaque from the SMPTE section.
Oh, great. Thank you.
Yeah. And also I'd like to thank AJ for hosting tonight, providing food. Shannon Schott and Kelly Rivas. And also I'd like to, it is the last meeting of our SMPTE season, encourage any non-members who are attending and who are appreciating the meetings and getting something out of all this to consider becoming a SMPTE member. You can go to SMPTE.org and look into that. So thanks, everybody. Feel free to hang out, talk to Tom.
Yeah, I'll be here till the end, and you can come up and see the videos. Be happy to answer any more questions that I have, or I can give you my card. We can, if you have ideas offline, we can talk. Or if you have video that you want us to train on, we can do that too.
Okay. Thanks.